Kunal bhaiya, I guess we can start. Uh, Let me introduce and
Okay,
then you can begin. Okay.
sure.
Yeah. Hello everyone. Welcome to the event When Numbers Lie, an event by VIT Mathematical Association, a session on how statistics are manipulated in ads, reports, and media. Learn how brands twist numbers, misuse graphs, and cherry pick data to influence us consumers and shape the public perception. Today, we have Kunal Sinha, fourth year BTech CSE Bioinformatics, Whitmaster's X Chair for the year 2025. And I welcome Kunal Bhaiya. Welcome to the meet. And let's
My
begin with the
pleasure.
session.
Yeah. Good evening, everyone. Like Ashwin said, I'm a fourth year. I'm currently doing an internship at ITPL. And yeah, so we'll start the session now. Let me just resize this. Yeah, this looks. Yeah. So, yeah, welcome to When Numbers Lie. Today we are going to talk about something that we all experience on a daily basis. Okay, whether you're in academia, whether you're a researcher, you're in the industry, or even if you're a layman, you know, buying something, we all experience this thing daily in our lives. So let's start. Firstly, can someone tell me what is a lie? What exactly is a lie? Anyone, just feel free to unmute and tell, or drop in the chat, guys.
Giving wrong information.
Okay, wrong information. That's good. Anyone else? You'd like to add something to this? Anything you'd like. It's not necessary that it's mathematical or something, but anything. What is a lie in general? Okay. Uh, to say something that you think isn't actually right. Okay, great. That is a good answer. Great. Yeah. So yeah, both of you guys were correct. A lie is something that is believed to be false by the speaker. Now, does a lie need to be false? If I'm telling a fact to you guys, does it need to be false for it to be a lie? Okay. So the answer is no. Lies don't necessarily need to be false. Okay. You can say something that is true, and it can still be a lie. Because there are very different kind of lies, and we'll get into that in a bit. So basically, there's something called lie of omission. Yeah, false statement with the intent to deceive. Great. That's a very formal definition. That's good. So don't necessarily need to be false. Okay. So that is the first thing that we need to keep in mind. Now, the second part, lying with statistics, is statistics. Now, what do you mean by statistics? A statistic. Tell me that. Do guys know what a statistic is? Have you seen a statistic? Have you studied statistics before in school or college or somewhere else? Okay, collecting and studying numbers, data to understand something. Okay. Others, what about you? What is a statistic? Okay, give an example of a statistic. I'll start with one. Mean, average. Average is a statistic, right? It's a measure of central tendency. Uh, Anyone else? What is another measure of central tendency other than average? There are two more. Okay. Yeah. Yeah, that is good, Shiva. Shiva Kumar, yeah. So, yeah. Do you know what is another statistic other than average? There are two more for central tendency: median and mode. Great, great, Arun. Yeah. So, basically, statistic is a term that can either mean the value or the function. So, a function is a statistic as well as the value that it generates on a given sample is also a statistic. We can't say that one is a statistic while other isn't. Uh, So I know it's a bit like confusing and a bit convoluted, but yeah, it is like that in the formal definition. So basically, how you calculate the average, the formula for average basically is a statistic, and the value that you get for a particular sample is also a statistic. Now, not just mean, median, mode. There are a lot of other statistics as well. You might have heard of skewness, kurtosis, or yeah, skewness and kurtosis are the most common ones. Other than that, correlation. Yeah, correlation is a pretty common one. So yeah, uh, moving on to the second part of this central tendency. Do you guys know what central tendency is? You might have studied this in school. Mean, median, and mode. Mean is the sum of values divided by total number of values. That is the total frequency. Mode is the value with the highest frequency. That is the most frequent value in the data. Median is just the middle value, that this side, the left side and the right side both have a equal number of values basically. That is how central tendency works. uh, if you guys have any confusion with this or you guys want a refresher of this, um, just raise your hand. Otherwise, I'll move on to the next slide. This was just a basic intro for you guys, just a refresher. I'll wait for like one minute or so. If you guys want to ask anything, just type in the chat. If not, we'll move on to the next slide. Okay. So, by the way, when studying something like placement data, which statistic do you think is the best? Which measure of central tendency? Mean, median, or mode? Okay. Arun, do you have any reasons why median is the best? Yeah, the answer is correct, but why?
When you study this, can you hear me?
Yeah, audible.
Yeah, so mode can also be used, but usually they use median or average. Median is usually better than average because, say for an example, if there are 100 students who were placed, and maybe 99 or very high number, 97, 98 of them got a really low package, less than 5 lakh, but only one of them got a really high package, say 3 crore or 4 crore. The average is around 20 lakhs or something, but 99% of those students have less than average. So average is not the best statistic. Median shows the reality much better.
Great. Yeah, that's a very great, good explanation for this. And so, if there's nothing else, we'll move on. So now, have you heard these two words anywhere? Skewness and kurtosis. Some of you might have heard. Skewness and kurtosis. Have you heard these two terms? I'm not asking if you know what they mean. I'm just asking, have you heard the term somewhere? Probability and statistics. Yeah, Saksham. That's great. Yeah, and ML. Yeah, great. So, skewness is basically the asymmetry of the probability distribution. That is basically where the modal value goes or where the graph goes in general. And kurtosis is the measure of how sharp the peak is, basically. So there are three type of plots, three type of graphs or distributions based on kurtosis. leptokurtic, normal distribution, and platykurtic. So normal distribution has a zero kurtosis, and leptokurtic have a positive, and platykurtic have a negative kurtosis. So there is a it's like a planar structure here. It's a measure of tailedness. So when you studying probability and statistics now, towards the end of semester, you study something about one-tailed test, two-tailed test, p-test, t-test, and all. This is this comes under hypothesis testing, and there you'll learn about this, the tailedness, what a tailedness is. Okay. Uh, so actually, these two are not mathematically important for us right now. It'll help us analyze the graphs that we'll see moving forward. And as you know, the skewness is basically whether the graph skews to the right or the left. Positive skewness means the graph goes toward the left, and negative means the graph goes towards the right. Any doubts on this? Just kurtosis is how peak to flat, and okay, not evenly spread. Yeah, sure, you can say that is the measure of asymmetry, basically. So yeah, okay. Okay. So, any doubts, anyone? If you want to ask anything, because this is still the basic part. We'll get into the main part after this. There are two more slides on basics. Then we'll get into the actual line part, how people lie with statistics. Okay. So guys, if you don't have any doubt till now, just raise your hand once. If you don't have any questions till now. Okay. Great. So, okay. I mean, it's fine if you people are interacting. Where do we use this? So, like Arun said, in ML, and while doing probability tests, also we use skewness and kurtosis. Uh, so, skewness and kurtosis, they help sometimes estimate market risk. Like, it's a very primitive measure of that. And while you're studying moments, MGF and all, MGF basically, moment generating functions and probabilities, you will come across these terms. Because I think kurtosis is the fourth moment, if I remember correctly, of in the MGF. And I mean, it sounds like gibberish. What I'm saying right now, but once you get into probability statistics a bit deeper, no, you will understand this. And yeah, so basically, it helps us make our models better based on given how the population is of the data, how the population distribution is of the data. So if this is done, I'll move on to the next slide. Yeah. Now, do you understand what a probability distribution is? Like, have you heard the term? Again, I'm asking. Hmm. So basically, probability distributions are like a map, you know. It shows the possible outcomes of an experiment and how likely each one is. So imagine you're rolling a dice, right? Now each number on the dice, 1, 2, 3, 4, 5, 6, has a 1 by 6 chance of coming. So that's a uniform distribution. Or something like, have you heard of binomial theorem? So basically, if you wanna ask in a like the binomial theorem, guys, do you know binomial theorem, right? Yeah, each test case is a success or failure, right? Yeah. So yeah, binomial theorem is we have only two possibilities, either true or false. So when you're looking into distribution where when x will be true, like for example, you throw a dice 100 times and you want to know when the number will be greater than 3. In that case, it is a binomial distribution basically. Or when you'll get 3 out of 100 times, what is the expected number of values you'll get 3, or how many times each you'll get 3. That is basically binomial distribution. So probability distribution is a function that gives probabilities of occurrence of possible events for an experiment. Now, as you can see, most of the probability distributions are linked. There are others as well other than these, but those are a very special case of these itself. And if not, they are limited to a very specific region of science that is only studied by those studying that specific region. So uniform distribution is when everything has a say equally likely sorry yeah, when everything is equally likely to appear. And another one you might have heard is normal or Gaussian distribution. So it follows the bell curve. I'm sure you guys are aware of the bell curve. It is a very popular curve, or the Gaussian curve, as one might say. So our main focus will be on normal distribution because we'll be going in a bit deeper into CLT, which is central limit theorem, which is on the next slide. Yeah. So central limit theorem says no matter what your distribution is, if your sample size is sufficiently large, the sample of the means distribution will be normally distributed regardless of the underlying population distribution. So basically what it means is if you have a very big sample, yeah, the distribution of the means will always be normal. That is what this says. Now, sufficiently large usually means 30 or more experiments or variables. Guys, do you understand this or you have any doubts? If you have any doubts, you can ask now. Mm, okay, so nobody has any doubts. You're understanding what I'm saying, right? Okay. No answer from that side. So, yeah, fine. So basically, what CLT says is if your sample size is big, usually it's greater than 30, and the sample means distribution will be normally distributed. So even if you have a hypergeometric distribution or something like a Bernoulli or binomial distribution, the sample of the means, the distribution of the sample of the means will be normal always. Now here I did an experiment, like it's a very basic experiment. You can try this yourself. Basically, I have tried this experiment with a bunch of data, and as you can see, as n goes up, it fits better and better into the normal curve. Yeah, that is the bell curve that you can see here. Be it a uniform distribution or an exponential one or a binomial distribution or a bimodal. So even as you can see, bimodal distributions, that is distributions that have two modes or two peaks, basically. When you go into a large enough sample size, they also become normal. If something that does not become normal after large size, you can take the log and it will for sure be in the log normal distribution. That is one of the tricks that researchers use while studying ML. Any people who are into ML here, you might know about this, the log normal or the log likelihood part. Have you heard of log normal and log likelihood functions or like distributions? Okay. So I assume everybody is understanding, right? Yeah. Okay. If you have any questions, feel free to answer. Feel free to ask me. I'll answer them now. Yeah, so it's a deep dive here into the exponential part. Now, do you guys know what a p-value is? Yeah, guys, do you know what a p-value is? Like, have you heard the term p-value less than 0.05 or greater than 0.05? Mm, okay, so basically in mathematics, we have this thing called as a statistical or probabilistic testing, right? So p-value is a measure used in hypothesis testing to determine the strength of the null hypothesis. Basically, null hypothesis is suppose here if p-value is less than 0.05, we'll say it's not normal. That is a null hypothesis. And if it's greater than 0.05, we'll say it's normal. We can't reject normality. So as you can see, as initially when we are at 0 to 100, you can see somewhere here it's very low. The p-value is very low. That is, there is a very low chance that it is a normal distribution. But once we reach above 100, once we go into the bigger numbers like 100, 200, 300, 500, the p-value goes way up, right? It goes way high, and you can't exactly reject normality here. As you can see, it fits pretty perfectly into the curve. And as you can see, the kurtosis growth tends to n, tends to zero. So normal distribution, like I said, has a zero kurtosis. So you can see here, excess kurtosis becomes zero. Basically, the peak flattens in a way. You can say that. The kurtosis grows to zero, and the peak flattens in a way. In exponential distribution, now this may be a bit different for other distributions which have a different type of peak, but for exponential, this is the case. Now moving on to the next part. I'm sure you guys are wondering by now, how do you lie though? Okay, this is a lot of statistical gibberish, like, you know, but how do you exactly lie with statistics? Uh, if you guys have any questions, please ask now. Otherwise, I'll go on to the next part. Okay, no one has any questions. You can drop it in the chat if you want. Okay, I'll assume that nobody has any questions. Okay, how do you lie though? So, firstly, let's focus on this graph, top left. Now, as you can see, the axis here starts at 96.5, and the difference between these three looks very big. It's like almost 3x. This is like 3x of this. C is like 3 times of A, and like B is 2 times of A, as we can see here. But is this true though? I mean, it is true, but like, what would a layman understand from this? If you remove the numbers from the bars here, what would a normal person think? Okay, C is the best option for me. I'll go with C because it's the highest score, right? But when you look at it like this, when the scale starts at zero, when it's a proper scale, you see that they're not that different actually. This is one of the main things people use. They abuse the baseline basically. Now for graphs and everything, the baseline is zero, right? For visualization and graphs and charts, it's zero. But sometimes companies and all, they abuse this part and they make it so that the baseline is not zero, and most people ignore this. Yeah, so this is the first thing. And second thing, the second most common way is Venn diagrams basically. Now, when you see a Venn diagram, and our assumption A normal person assumes that the bigger the circle is, the more the population is there, which is not true. And but a lot of people fall for this. The smallest circle might have the largest population. Yeah, area is proportional to value, which is false. I mean, which doesn't need to be true. Uh, so that is one more case. And second part is variable. So basically, variable access. There are two variables here, x and y. Now, they might not be related at all. This might be the number of cancer patient, and this might be number of people drowned. Okay, these two might not be related at all, but sometimes what people do when publishing a research paper or doing any study, they make graphs like these. Now, as these people, like, it has a perfect negative correlation. Okay, we can see that like if variable x is going up, y is going down. Like you can see it, the nature is there. Variable y is going down and x is going up, basically. So there is a perfect correlation, a perfect negative correlation here, but they are not they are not in any form of causation. Okay, so this is one of the most significant, things. And yeah, sorry. Okay, I don't know how that works. Yeah. Um. So next, let's get back to the first question I asked you guys. X drug reduces the risk of a heart attack by 50%, but it's 10x as expensive as Y. How many of you buy the drug X and how many of you stick with Y? Yeah. Come on, guys. Answer this, please. Like, this, okay, I revealed the answer. That's what I should. Yeah. So, X, okay. What about others? Just raise your hand if you buy X and don't raise it if you buy. Buy. Okay. Others, what about you? Would you buy X or would you buy Y? Okay. So, are there any reason for changing to X or
No, I stuck with X in the starting itself, the more expensive but more effective one.
oh, okay. So yeah, any reason for like changing from Y to X? I'm asking that. Like any
Uh,
reason
s-
for that?
uh, See, since it's a really important matter, and
Yeah.
50% is a huge number, though it's 10x expensive, 50% is a huge number and it can save lives. So, yeah.
Okay. Now the thing, the catch is here. What exactly 50% means to us? Okay. You'll see in the next slide what I mean. But yeah, let's see. So baseline risk, that is Y. Risk of uh, Y reduces the risk by 2%. Now there is a 50% increase in that. Basically, that risk reduction risk increases by another 1%. That is 50% of 2%. So out of 100% patient, like 100 patients, only one more person has had their heart attack prevented. So basically, I think somebody said so. Okay, you raised your hand again. Mhm. So, just a second. Okay, how to? Yeah. So, baseline risk was 2%. That is, Y has reduces the risk by 2%, and X increases that 2% by 1%. That is 3. Now, if there is a 97 and 98% chance, Arun, would you stick with Y or would you still change to X after
No,
knowing
I'll,
this?
I'll, I'll, I'll say I'll still take X because this is in the case that I'm a normal patient, then 2%, 1%. But if I'm already in heart patient, that's way more than 1% or 2%. So if I'm already in heart patient, then I'll stick with X.
Okay, you stick with X. But
Yeah.
Yeah, for most people, buying an expensive drug that is labeled as 10x, that is labeled as a 50% increase, you know, and for most people, it won't be possible given how much medicine costs these days. For example, if Y was like 1,000, 1,500 rupees a month, then X would be 10,000 or 15,000 rupees. Okay. So for most people, it won't be possible to buy that expensive medicine, right? Because we are a very very big country and not everybody has the resources. So this is one of the ways that companies false advertise. Now this is not just like, you know, hard, not related to medicine, not just related to medicine I'm saying, but if you're buying something that says it has 50% less sugar, okay, now that is also a case. It might have like 1 gram of sugar per 100 grams or 1 gram of sugar per 10 grams, and reducing it by 50%. 50% is 1 gram is zero point 0.5. So it's zero point 0.5 per 10 grams. It is relatively healthy, but still that's a lot of sugar, right? So this is one of the things that companies use. And yeah, now this is something very interesting. Uh, if you guys want, I'll give you a hint for this. A cancer test is 99% accurate, and someone tested positive. What is the probability they actually have cancer? Uh, Anyone, can you answer this or try to answer it at least? What is the probability that the person has cancer? Assume that 0.1% of all people have cancer in this world. Yeah, just write it. Point. Probability that a person has cancer is 0.1%. Right. Now, a test that is marketed as 99% accurate uh, is a very good test, as you might say. But like, the cancer chances are 0.1%. Like a probability a person has cancer is 0.1%. So, okay. I won't ask you guys to calculate this actually, because it uses Bayes theorem basically. Okay, and I'll show you the calculation on the next page. So if prevalence, that is, there are 90, like 0.1% of the people have cancer in this world. Bayes theorem gives a probability of 9%. So you might be wondering how this is calculated. I'll just show this to you on Desmos. Like, Desmos. So what we're saying is yeah, 99% of the cases are true, right? Times only 0.1%, so 0.001 people have cancer over 0.99. That is 99% of the test cases are true. 99% of the, like, accuracy is 99% over 0.001, 001 plus what is the next thing? The next thing is the false positive. Okay, false positive is when you don't have something, but the result gives a positive anyways. Result is positive anyways. So basically, somebody doesn't have cancer, but the test says, okay, you do have cancer actually. So yeah, moving forward with that, um, it's gonna be 0.01 times 0.999. Okay. So as you can see, there is a 9% chance. So I'll just multiply this by 100 to convert it to a percentage. There is a 9% chance for a test that is advertised as 99% accurate, right? If it checks, like if it gives you a positive result, there is only a 9% chance that the person actually has cancer. Now, that is a very, bad result, because having only the 9% probability to actually tell whether somebody has cancer or not. So this is one of the more common false advertisement that people see, or people like see in their daily lives, and this can be deadly too. And this is common in publications as well. There is another section in the PPT. I'll go into that. Huh. Now, Arun, I think you gave an example for this, right? So yeah.
Yes.
Suppose there are 10 employees and 9 of them earn 3 LPA, and CEO earns 1 crore. So the company might say that our average salary is 12.5 lakhs or something, right? And people might fall for that and go for interviews and sign the documents and all. But the actual salary might be 3 lakhs. Just because the CEO earns 1 crore and he's an employee, he considers himself an employee. The average salary will look like 12.7. But in this case, median is 3 lakhs, the typical employee's reality, right? And mode, what most of the people earn. That is 90% here. Yeah. So what most of the people earn is 3%. So this is very common, a reason people avoid averages. Another thing that is not written here is average is not a mathematical term. Okay. So whenever a company says to you average, they can choose any of the mean, mode, median data, any measure of central tendency usually, to tell us which suits their needs the best. Basically, if they want to show something as high, they can show average. Like there are some places or some institutes or something that may show their average package is very high. Okay, but it might be like Arun said, only a few people are getting a good package, while most of them are getting like 5, 6, 4 lakh packages. And that good package is good enough to offset the average enough that the average package becomes fairly high. And that is what happens here. This is something that everybody might have seen. A few years, like 1 or 2 years back, you might have been applying for colleges and you might have come across this. I mean, that is the time most of the people come to know about averages and medians and mode while getting into this stuff. So, yeah, we'll come to the methods now. How to do this? Like, how do people do this? One is cherry picking data. Now, what do you understand by cherry picking? Have you heard this phrase somewhere, cherry picking?
Choosing only beneficial data.
Okay, great. Yeah, both of you are correct. Great, Abha and Arun. So basically, cherry picking, like you guys said, is only picking the data that benefits our conclusion. And let's move on to the next page. Right. As you can see, cherry picking means selecting data points, time periods of studies that support a predetermined conclusion while suppressing contradictory evidence. It is the most pervasive form of statistical manipulation because it leaves the selected numbers entirely accurate. This is what I meant by saying that like lie need not be false. You're just looking at different things instead of looking at everything that we have. We are just looking at a small set, and for that set, the given statement is true, right? So a good example of this is the publication bias. Now there was a research by Turner et al. And which examined the antidepressant trials submitted to the FDA. So 38 studies were examined. 38 studies showed positive results, and 36 showed negative. As you can see, of 38, 37 were published, but of negatives, only 14 were published out of 36. So this is something that happens on a daily basis. See, scientists often say, you'll often hear the professors and everybody say, कि any result is a good result or no result is a good result. You just need to do the experiment and show whether there is a relationship, no relationship, or a negative relationship, inverse relationship basically. But that is not how the research scenario is right now or has been for a long time. If you say something has a negative effect, there is a very high chance that it might not get published. Uh, I have seen this firsthand as I had a few papers that were rejected before finally being accepted. because the result showed that three of the four variables we were handling had had no relationships, but one variable had a relationship with the others basically. So the fact that we said there was no relationship made it very hard for the paper to get published. Now we could have done this part, the cherry picking part, taken only the data that suited us, and went for the publication. But like in more or less after some time we were able to get the paper published. So secondly, this are some examples that you'll see. uh, yeah. Mm, okay, so this is what I said from the, yeah. Okay, this is, oh yeah, this one is, wait, yeah, cherry picking is here, sorry. So as you can see, 37 positive studies were published, 14 negative studies were, and 22 were suppressed. So this is one of the leading causes of people not relying on research papers. Another one being irreproducibility. So most of the research work that you see these days cannot be reproduced in another setting other than the experiment. Other than the given experiment, they can't reproduce those results. Even if they are said to be general results, they can't. And in some cases, even in the given experiment itself, you can't reproduce those results. So there is something called a Bonferroni correction. So I mean, if you use any online softwares or databases, you might come across this, and you might come across as the FPR, to false positive rate. And there are a few other correction like Benjamini Hochberg correction and all. You might come across those terms too. So these terms, if the error rate goes too high, the correction basically, it's a formula, it's a method, and that method sets the error at 5%. Now 5%, as you remember, our p-value cutoff should be 0.05. So it makes that our correction is just around the limit, and the results can be published. It's not a bad thing, it's a good thing in some cases, but you use the use of this can be abused. A lot of people abuse these kind of things when publishing research work these days. And yeah, moving on to the second part, survivorship bias. You might have heard this term somewhere. Like, this is a very common term. I think there was this YouTuber Zach D Films. He makes like short form video. He made a video on this sometime back. Somebody sent it to me. Do you know what survivorship bias is? Did you guys take something? Okay, somebody should. Yeah. Do you guys know what survivorship bias is? Have you heard the word somewhere? Okay. So, yeah. This thing was discovered, or this thing was noticed, more or less, basically noticed around World War II. So we basically, planes that I show the image. The planes that were coming back from the war had most of the bullet holes near the wings, but there were rarely any bullet holes near the engine or the cockpit. Huh. So what happened is the statisticians at the institute in America, they started suggesting that you reinforce the wings because they have holes, and they have the most chance of for failing. But what they missed was the planes that had like strikes on engines and cockpits were the planes that didn't come back, or the people of the pilot they died. Okay, so this was something that they missed earlier. And then there was this person, Abraham Wald. His insight was the observed planes were those that survived, and cockpit hits were the ones that crashed. Okay, the data was conditional on survival, not on being hit. So basically, another one is startup. So startups. You might heard of the have heard of the startup trend right now. A lot of people are doing startups and everything. Now there are thousands, if not like millions, but like hundreds of thousands of startups now. Okay, people register their own companies and everything every day. The process has been made so easy now. So a lot of those startups fail in the early, first year or second year. A lot of those startups fail. As you can see, by year two and year three, almost the number is cut down to almost a third, right? So this is the survivorship bias again at play. We hear only from those startups that are successful. We usually don't come across the stories of the startups that fell behind. We don't know what they did wrong and what went wrong with them, what the ideas were. Most people don't come across these. They only focus on this part. Year 5 and year 10. Hmm. The startups that survived. Now, this is still a pretty good number compared to 10 years ago, right? But it's still a very small number considering that only 10% of startups made it to year 10, while others had, like, succumbed to bankruptcy or some other issue. And yeah, so like the fewer the number of survival, the higher the survivorship bias, basically. Um, and data dredging is not so much of a like statistical thing. I'll show it to you. I think you'll understand it. By the way, any questions as of now for these two methods? Anything you'd like to ask about them, or anything you don't understand? How or why we are doing something? You don't understand? Just share it here. Ask away. Don't like feel in. Mm, okay. So I'll give you guys a bit of a like 2 minute break, and then we'll come back to data dredging. In the meanwhile, guys, are you guys understanding the session? Do you have any doubts? If you have any questions or like anything you don't understand, you don't like, something like that. Okay. Okay, by 23, we'll start again. Mm, it's 23 now. A few more seconds. Let's start. Yeah, it's 23 now. So if you don't have any questions about the previous thing, I'll start with the next part. Okay. Now, the data dredging is more of a technical trick, but it's really important that you know this and you study this because p-value, like I said, helps us with in realizing whether the result is significant or not, whether we can reject the null hypothesis or not, right? So the common threshold that we see for p-value is 0.05, that is 5%. And so what 5% means, let's go into that now. So 5%, it means ki if there was no real effect, there is a 5% chance, under normal circumstances, if there is a 5% chance of seeing this, extremely random event, like it basically means there is a 5% chance of this event occurring. Okay. Now, the event may be extremely rare or anything, but given the circumstances that the conditions are satisfied, there is a 5% chance. So that is a cutoff basically. If it's more than a 5% chance, we consider it significant. If it's a less than 5% chance, we don't consider it significant, basically. Right. So data dredging occurs when a researcher tests many hypotheses on the same data set or makes many flexible analytical decisions until a significant result appears. Okay, so data dredging basically what it means is, suppose you have a data set and you say you'll do 100 tests on that. Uh, Now you don't have any particular problem in mind while using the data set. You just say I'll do everything I can, and you found one of the results to be good. Now pretending that that result was the pre-specified hypothesis is the issue is called data dredging. Basically, you make multiple comparisons, you do a lot of testing, and you find something and you manufacture a discovery that it is accidental. Now, thing is, data dredging is not inherently wrong. Okay, a lot of younger people or newer people do this if they don't know the methodology or like how research works basically. But what it leads to is that people who do this are not able to get a good insight into data even into the later years. Because they're not able to specify hypothesis and deal with the p-values, right? Because p-values as a whole is a very important concept, and t-testing, like hypothesis testing, is a very important concept in all of science, not just physics, chemistry, biology, like all of science and mathematics, and even social sciences and sociology. They also use p-values to check the statistical significance. Right. So another example is this one. Simons, Nelson and Simonson, they had a paper, okay, uh, demonstrated that statistical analytical flexibility allows researchers to prove listening to Beatles when I'm 64. There is a song "When I'm 64" by Beatles made the people 1.5 year younger. Hmm. Now, is this possible in real life? Do you think listening to a song can make you a year and a half younger? No, right? So this is another thing. Like it's correlation and causation at play here. But yeah, this is what happens when you do data dredging without thinking about the consequences. Because hypotheses don't know what, like, if you don't make the correct hypothesis and you just data dredge and like prove it somehow, your result will definitely be wrong. There's a very low chance it will be right, but even if it is right, you won't know how to explain the results in that case. Yeah, as you can see, flexible covariate inclusion stopping rules. Basically, they doctored the data to look like this to show that data dredging can, like, allowing analytical flexibility to prove something that is false can be done. Okay. Okay, why is this image crashing? Never mind. So, next part of this is regression to the mean. Now, do you guys understand regression? What regression means? You might have heard this word somewhere. Regression. Anyone, you can unmute and say. No issues.
It's used to model the relationship between two variables.
So just two, or it can be more than two also.
No, it can be any number of variables. Yeah, it can be any number of variables.
Okay, great. So, Arun, do you know is like regression is a part of ML, right? So, is it supervised or unsupervised?
Regression is supervised.
Yeah, great. Yeah. So, as you said, regression is a type of supervised learning, and you use a set of variables to determine what exactly the outcome would be in the future or in the past, right? And basically check the dependency of one or more variables on each other. Yeah, this is a very interesting one because remember, you guys remember, right? When everybody was studying for JE or VIT exam or whatever, and everyone was looking for coachings. Now there were coachings that claimed that our this is like 15% higher, or we have this many more students. Right. Now the thing is, it should take the bottom 25%, right? And you ask them to write an exam for you. Great. So and they scored 10% on that exam. On an average, let's assume they scored 10%. The bottom 25% of students, that is, they score 10% on an exam. Like they score 100, 10 out of 100 marks, basically. Now you give them coaching, okay, and you send them to the coaching, and they have a 15% improvement. So 15% improvement is basically, can anyone tell me how much? What is a 15% improvement in 10 marks? 11.5, right? So basically, after going to the coaching, the person scored 11.5 marks. Now, 15% sounds much higher, right? But given somebody had scored 10 marks, scoring 11.5 is not that big of a deal. The teacher could have been different, and even if it's a objective type question, you could have just made a fluke. The person could have made a fluke. But ignoring that, even if we are ignoring that, suppose a person gave the test again and his score was 10% higher, that is 11 marks. So the person who spent money on the coaching and who went to the coaching, that advertised 15% improvement. But the person, when he gave the exam again, another person, when he gave the exam again, scored 10% more. So the only improvement the coaching gave him was basically 5%. That is 0.05 or zero point 0.5 marks in this case. As you can see on the graph here, uh, so basically regression to the mean, what this means is कि we have a regression on our hand at our hand, but we just use a single variable or single mean to account for the whole thing. But as you know, with regression, this is not the case, and this will lead to a lot of error. As in regression, there is a lot of variation that we have to account for, and when we don't do that, it leads to error. Hmm. Failure to account for this creates the illusion that treatments are effective when they are not. Hmm. Like I said, a treatment is 20x more, 20% more effective, while a person that is recovering can recover like 15%. So it's like 5% more. Now I understand it's a health thing and people will go for that 5% too. But given the cost and everything combined, is it really worth it for the experimental studies? And there is a chance for failure too in that if it's an experimental study. So this is one of the things, regression to the mean, right? And RTM effect, regression to the mean versus reliability. So basically, the bigger the improvement is, you can say the lower the reliability is. Hmm. The larger the number you listen, ki, okay, there was this like 80% improvement in marks or 90% improvement in marks of somebody who studied at XYZ coaching or XYZ college. So that is more or less a scam, or it's not exactly a scam. It's like they're using the data that suits themselves. We studied cherry picking, right? A few slides back, collecting only the data that is beneficial to us, cherry picking. So they are doing that in mixture with regression to the mean, RTM, to get a favorable result that they can publish. Now, I have seen a few cases where people, no, this is not true for big companies, they usually calculate the means and everything, but for a smaller businesses, okay, they don't have the resources to do a statistical analysis of their work. So if the owner is not, like, if the person in charge is not into statistics, they can't do it. So they make up random statistics. This is very common in India, and they make up random statistics. which is a really bad thing. Yeah, one example of this is Reebok. I think they released some stones a few years back. So they were said to improve athletic ability by 12 to 15% if you rub them on your skin. This was like pretty old, it's like 20, 30 years old thing. Uh, Reebok or Adidas, one of the companies, right? And they got sued for that because it wasn't the case, and like that was a very big scam that they kind of pulled off, but tried to pull off basically. Now, Simpsons paradox. This is a very interesting one. So, suppose there are two teams, one and two, right? Uh, and we look at each game. So, it's like win, loss. Okay, so it's win, loss. Yeah. So, looking at this, given that the overall win is based on the score between one and two, can you tell me who won the game based on this? Suppose there were three matches, and the overall winner is decided based on the total score in three of the games. Now, based on this, can you tell me who do you expect to win? One or two? Who do you think would win? Oh, Ronnie made the message. Yeah, great. Yeah. So, guys, anyone, uh, do you think like who would win, one or two? One lost two matches, two won two matches. Two is more likely, but it can be either way. Great. Arun, why can it be either way? Can you explain a bit in detail? Why do you think it can go either way?
So, since even though one has lost two matches, but the margin of difference in their victory can be greater than two's margin of victory in both the other games combined.
Yeah, so great. So when a layman or a normal person will look at it, a person who is not like who doesn't understand this part, what are inside it, can we look into it? They might think, okay, two is more likely to win, just cause two has the better amount, two has the more number of wins. Yeah. Yeah. So just because two has more number of wins, person might think that they are more likely to win the overall game, right? So Simpson paradox occurs when a trend appears in several subgroups, but the data reverses or disappears when the subgroups are combined. So there is a lurking variable. Okay, there's a lurking variable in this case that people fail to account for. Okay, you see the data and the trend that you proposed hold true for the subgroups, but there is some sort of variable that you have forgotten that reverses or makes it and disappears uh, in a larger subset or when all those subsets are combined. Huh. So a good example is a medical treatment. So basically, you guys know what a placebo is, right? A placebo is basically, how can I'll tell you guys placebo? I don't remember the exact definition. Are you guys aware of what a placebo is? No? Okay. So placebo is basically a substitute that doesn't actually do anything. Hmm. It's just a psychological experiment done by doctors. So suppose there are two medicines and two people are given the plus. One person is two sets of patients. One is given the placebo and one is given the new medicine. Both are being told, ki, okay, it's the new medicine and you have to eat this for the next month. Okay. Now the placebo group shows better results than the other one, than the medicine one. What this means is ki the placebo, I mean, it doesn't mean the placebo is performing better. It means that the medicine actually makes the condition worse compared to natural healing for most people. Right. Now, the thing that happens here, as you can see, where was that graph? Yeah, this one. Both groups. The top middle graph. So, as you can see, when you model the relationships or the regression of this data, two groups will give you a positive regression or positive relation between these two. Right. Okay, you see there is a positive relation here, there's a positive relation here. But when you combine these two groups and map it overall on a regression line, the regression becomes negative because of the how the groups are placed. Right. So this is a very common thing. This is not a very common thing, but this is one of the most, like, things that people who are into statistics, who have studied it for a long time, even they might miss this sometimes. Uh, this is something that is a genuine mistake that I won't say is a method of lying. It's more of a genuine mistake that people fail to account for. No, people do lie using this. See, as in this case, a lot of mild people who were, supposed to recover quickly on their own were given the placebo, more placebos, and lesser drugs, right? But the overall, and like as you can see here also, severe drug and severe placebo, lesser people were given placebos too. But when you combine them overall, yeah, when you combine them overall, you'll see overall drug was given, like drug appears better. But when you split into a smaller subsection, that is mild and severe, it appears worse. Now, this happens just because in the case where it is severe, sorry, mild, or like it's non-existent, they might have given it, like, to a lot of patients there, and it skewed the result here. So people who barely had the disease were given the drug, who had a mild disease, and they took the drug basically, and they recovered quickly. So this skewed the results to show that. And when we are considering medical disease, like medical studies, one thing you should keep in mind is to always have the severity groups in mind. Whenever you're reading a medical research paper, keep in mind that you look into the severity groups as well, and what the sample size was, and basically look into how the data was curated and where the data was made, where did they get the data from. Uh, this is a very common thing that people, again, I'm saying it, people miss this a lot, and it can affect the results that you're experimenting for, you're trying to get basically. Yeah. Second part. Now, this is a very common meme. You might have seen this meme, Texas sharpshooter fallacy. Have you seen this meme sometime, like on the internet anywhere? The person shoots the board and then makes the, like, what is this, goal around the holes that he has shot, basically. Okay, so it's a very common joke in, like, uh, it's a very common joke basically. So if there is a guy in Texas, USA, who shoots a gun at a wall and then draws the target around the bullet holes and declares himself a sharpshooter. Hmm. So basically, in statistics, what this means, when patterns are identified in data after the fact and then presented as if they were predicted before the data was collected. Basically, you're saying, okay, I have 100 things. I predicted these things based on, I predicted X based on Y. Okay, and what happened is you predicted Y based on X. You go backwards. Now that is something that is not always true. Again, I'm saying, because if something is related, like one way, it is not necessarily related two way. If X depends on Y, true, but it's not necessary that Y depends on X. Hmm. This is one thing that a lot of people miss. Yeah. So a classic example that you can see is cancer cluster. Cancer clusters that we see. So basically, what happens is this doctors, when they look for skin cancer clusters on a patient's body, if you look at enough regions, there is a high chance key clusters will appear purely by chance. Okay, they might not even be cancer clusters. They'll just be clusters that you'll examine in the you know MRI scan or something, and they'll appear purely by chance. So that is an example. So basically, they were looking for something, and they saw a cancer. They saw a cancer cluster or some cluster, and the doctor said, "Okay, we were looking to the cluster, looking at the cluster itself." Hmm. So yeah, expected number of lucky predictors. So basically, suppose you're some sort of agent or something, analyst, working for a very big stock firm, an HFT or something. Now there is one guy at your firm. There are 5,000 people at your firm, and you have worked there for 10 years. Now there is one guy at your firm who is a genius and who has predicted every single fund correctly till now. Now, K correct. Basically, every correct fund given luck. It's pure luck. It's like a random basis. So it's half to the power of K, because each fund can either go give you a profit or a loss in a way. We're not accounting for how much of a profit or a loss, just a profit or a loss for now. So expected analysts with K straight wins is number of analysts into half to the power of K. This is the expectation formula, right? So if N is 5,000 and K is 10 years, out of 5,000 there will be 5 analysts, and basically what this means is okay, even if you do it by chance, if you have a large enough sample size, there will always be people who will profit every single time. And the thing that happens here is people like to portray them as geniuses and all. But even if all the traders in the world were doing trades randomly, there would be like 5 to 10 people. I mean, yeah, there would be a lot of people who made profit on every single trade. Huh. This is more so how the information is twisted rather than it actually being false. People think, okay, these 5 people know the market the best. It could be they are just lucky in a way. And now coming to the this part, correlation versus causation. Now, does correlation equal causation? Do you know this? Have you heard this somewhere? Okay. Correlation does not equal causation. Great. But why? What does correlation mean and what does causation mean?
Correlation means that if two variables, say x and y, are going up or going down together,
Hmm?
then they're correlated. But if we can only say that it's caused by the other variable if x is going up because y is going up, or x is going down because y is going down.
Okay, great. So correlation is basically how much two variables associate with one another, or like how much they're dependent on one another, right? Uh, so that's a great answer. And in analysis of like when we're analyzing data, correlation, a measure of correlation is like Pearson's coefficient of correlation, or there's a rank coefficient of correlation as well, with correction, and we use a lot of others too, depending upon which correlation we are looking at. So there are single correlation, multiple correlation. Mm, Causation is basically something like, okay, you left food out for 2 days and you ate it and you got sick. That is causation. The bad food caused you to get sick. Hmm. But suppose something like, you came back from your work and then you ate bad food and you got sick. And now this happened a few times, like 4 or 5 times. So does going to work make you sick? Because every time you came back from work and you ate the food, you got sick. So does going to work make you sick? No. But if you analyze the numbers, it will say, yeah, going to work makes you sick. A very common example is Nicolas Cage. You might have heard of him. He's a very popular actor, and This is one of the things. Actually, this was one of the graphs that got me started in learning statistics, because I was giving an interview and one of the questions was on this, falling into a pool, and film Nicolas Cage appeared. As you can see, the years where Nicolas Cage makes more movies, more people drown. It's a straight up positive correlation here. Hmm. But do you think this is actually true? Can people really drown because Nicolas Cage made a movie? Was the movie so bad that it made people drown themselves? No. Guys, what do you think? Was the movie so bad that it made people? Okay. Oh, and okay, wait. This is not the last slide. Sorry. Yeah. And another is time series manipulation. Arun, it's not exactly related to overfitting. Uh, it's actually about the bias that a person, being observed may have. Okay. This is more of a philosophical thing rather than a mathematical concept. I added this here because it was like Hawthorne effect and observer bias, Goddard's law. These things are a bit more psychological and like philosophical. Yeah. Time series manipulation is, suppose, okay, where is that thing? Yeah, this thing. Suppose your graph looks like this. right? So your graph looks like this. This is your stock. Now you are asking investors to. This is the zero. Okay, this is zero line, and this is like the stock price. Now you are asking investors to invest in a startup. What you have seen is the trend here. Do you see the trend? What is happening here? Yeah. Do you see what the trend is here? It's suppose here they got funding, they went bankrupt, they got funding again, they went bankrupt. This is a certain startup, like this is some startup, random, any random one. Okay. Now they got funding, they went bankrupt. They again got funding, but they showed only this part. Huh. Again, they when they were asking for backing, this thing funding again, they showed only this part. And now when they're asking funding, they're only showing this part. So there is no real profit or loss here. The startup is just losing money. There is no real profit here. The startup is just losing money here. But when the startup when get asking for funding might show, okay, there was this person before us who ran the startup. He bankrupted the company. Now we have started raising money and we have made this much money. Well, this must might just be the funds or the grants that are received. There is no real profit here. And another one is like, okay, confounding variables is a whole another can of worms. Like, I'd rather not go into that. It's a very deep topic. Oh, small sample sizes. So, do you remember the law that has said the CLT, central limit theorem, has stated sometime back? Everything when you take a large enough samples becomes normally distributed. So this basically goes into that. So sometimes what people do is they cherry pick the data, like we said, and it leads to yeah, small sample size. Yeah. So from the data that we have, they only cherry pick the top 5% or top 10%, and they basically make them, make the results appear in their favor, so that they can publish a research study or market the product better. Yeah. So like I have a few questions for you guys. Like I gave in the middle, right? So I'll ask those, and then in a few minutes, uh, let me start. Yeah. So have you heard this phrase? 9 out of 10 dentists recommend Colgate, or 8 out of 10 dentists recommend Sensodyne or something like that. Have you heard this phrase somewhere? Guys, come on, raise your hands if you have heard this somewhere before. Okay, great. Arun has heard it. So yeah, what happens in that case? Do really 90% of the scientists recommend? The thing is, virtually all toothpaste formulas are the same except for the sensitive ones. Basically, the ones that deal with sensitivity. Other than those, most of the toothpaste formulas are the same, with a few gimmicks added here and there. So what happens is, when you ask a dentist for a recommendation, they'll say any toothpaste, or they'll list the top five brand on the top of their head, huh, and they'll say, okay, these 5-10 brands are there, they are trusted, and you can go for them, or they're like big brand, they don't compromise with quality, you can go for them. The thing is, when this kind of claim is made, that 9 out of 10 people recommend us this, what is happening is those people have recommended other things too. Somebody has recommended Pepsodent, somebody has recommended Sensodyne, somebody has recommended Colgate. Those people has recommended multiple things, but the person who is claiming that they have recommended 9 out of 10 people have recommended us, which is true, but they fail to mention that they have recommended 10 others along with them. Huh. So this is one of the more like simpler ones that people fall for. Huh. And okay, I have a few more written, just a second. Yeah. So coffee. Basically, I'm saying three statements. Okay, tell me which one do you think is the like which one thing would you start doing? Okay, out of the three. Now, coffee reduces Alzheimer risk by 95%. Red wine linked to lower heart disease rate. Paracetamol found to cause depression. Now, which one of these things are you most likely to do? First, second, or third? Guys. Okay. So this is an example of correlation versus causation. Again, suppose there are like people who drink coffee on a regular basis. Suppose like they tend to be richer than other people. I'm not saying they are. I'm saying an assumption. Like we can assume, for example, for now. Okay, now this statistic is not real. I made that up. But people do make this kind of stuff up. Okay, so when you're dealing with something like this, it's a correlation versus causation kind of thing. I took a data from some time and I just sampled the data that suited my needs right now, like when preparing for this session. And I took the Alzheimer data and coffee data, and basically I sampled only data which gave me this result. So it's basically cherry picking on top of correlation versus causation. So I took only the data that gave me the best possible result for my claim, and I showed the claim, and that is it. But which is a very bad thing. Like, okay, uh, yeah. So another thing is when you have seen this thing, brands use 70 or 80%, like say 70% off, up to 70% off. The thing is, up to means it's like max of 70%. There is no necessity for the thing ki there is actually something that is 70% off. Okay, even if it's like anything, there is no requirement for the thing to be 70% off. It may even be 0% off, for all we know. That is one of the common tactics used by brands these days. Like this is more of a clothing brand thing, but yeah. Then again, speeds up to 1 Gbps. This is also another common claim that we have seen in our daily lives. Speeds are not up to 1 Gbps. They'll usually fall around 500 or 600 Mbps, which is not slow but not the fastest either. So this is another form of the claim that we have seen. And yeah, I mean, other than this, I mostly went through most of the things that were about this. If you, I have a document prepared for this actually. Wait. Uh, what? Yeah, I have a document for this. If you guys want this, I have like added the formulas and everything in this about the event. If you guys want this, I can share it with you. It has a lot more methods. It has like 20 something methods of how people manipulate data. Hmm. Misleading visualization, error bars, confidence intervals, heat maps, and everything. And it has a few case studies as well. So, like I said, Reebok one. So, Reebok Easy Stone made leg muscles tone 28% more than ordinary walking shoes and strengthen hamstrings more 11%. Now, this is a very small, like, this was done on a very small group of people, and they actually got sued for this. Like you can see, it's the largest FTC deceptive advertising settlement of 25 millions. And yeah, another one was the clean diesel one. You might have heard of this one too. This was also pretty popular. Then Colgate, I already said. Kellogg's first. This was done again US based. This was not in India. Yeah. So there are some like other parts to this session. Like if you want to go into the detail of that, you can. I'll share this document if you'd like, or you can DM me or one of the board members. They'll share this with you. And yeah. So whenever you're dealing with statistical data and you think claim might be wrong, this is the framework that you should follow. Baseline. Okay. So what are we comparing it against? That is a baseline. Absolute versus relative. Okay. Is it absolute or is it relative? Absolute is basically ki, is it like if it says 95%, is it 95% to the starting point or is it 95% to the competitor? Huh. Sample, how many subjects are there and how were they selected, and is the sample a good representative, it should say a good representative of the target population. Independence, and independent, this is not a mathematical point of view, it's more so like who profits from this thing. If the study gets published, who profits from it, basically. Context. So what are we exactly looking at, and what should be the exact data that we need to make this claim. Okay, having the relevant knowledge or the context, as you know, is an important thing. And causation, so this is the correlation part. See, after you have done the basic part, I mean BASIC part, you can get the correlation. But does the correlation have an actual causation? Can it imply that? What are the variables that confounding variables that exist? So this is basically the framework, or like these are steps you can follow to avoid this whole thing, to avoid being scammed or falling for this kind of thing. Yeah. So conclusion and all. These are the references I have used. If you would like, I can share them with you. Um, like Goodhart's paper is here, Cohen, Bettelman, and others too. Like FTC, the Trade Commission for Kellogg. Basically, it was against the conflicts. There are claims on sugar. There are a lot of other ones too. If you want, like, if you go through this, you'll see that. So, any questions that you guys have? Yeah. If you guys have any questions, you can ask now. If you don't understand anything,
Hi, sorry to interrupt, but the attendance form is in the chat on the Google Meet, so everyone please just fill that up.
yeah, guys, let section said. Make sure to fill the attendance form. Um, Once you're done with the attendance form, just give a reaction in the meet, like a thumbs up or something. Anything is fine. Uh, okay, great. Guys, did you understand what I explained today about